Hi everyone, thank you for coming. Today's talk is being given by Pierre Verlinden, the Chief Scientist of Trina Solar. Pierre spent many years in the solar industry, beginning at SunPower in the US. He was there for about 11 years as the Director of R&D. Pierre then moved to Australia, the lucky country. And he has worked in solar systems and Origin Energy. And I think you're involved in the sliver technology.
Yeah.
And also Managing Director of AMROC in Australia. So now Pierre's here today to talk about cost analysis of current PV production and strategies for future silicon PV modules. Pierre also is originally from Belgium, and he has a PhD and Masters in Electrical Engineering. Over 90 papers, 10 patents, and a lot of contributions to books throughout the years. So please join me in welcoming Pierre today.
Okay, thank you, Linda, and good afternoon, everyone. Thank you very much for coming so many people today. It's very impressive. Thank you, and well, thank you for inviting me to give this talk. For the people who were in Paris, the EU PV-SEC, unfortunately, you're going to see exactly the same talk, and I'm sorry about that. But for the one who were not there, well, it's going to be the first time, and thank you for attending. So the interest and the topic of this talk is to look at the real cost. And a lot of people have been talking about projections, talking about learning curve models, etc. And I wanted to compare those models with real data and see where we are today and where we're going in the future and what would be the strategy for the future. So I want to start with a short introduction about Trina, for the people who don't know Trina Solar. Trina Solar is today the number 2 suppliers of PV modules in the world. That's by numbers in terms of gigawatt. In 2013, the official number is not out yet, but the estimate is about 2.6 gigawatt. We have a total capacity at the end of 2013 of 2.8 gigawatt. So that means if you calculate right, we are completely maxed out for the moment in production. We're putting online something like 1.5 gigawatt of new capacity this year. So you see the distribution of our product, the destination of our product, that was in 2012. Germany in 2012 represented still the largest customer. Today, China represented the largest customer. Japan and US, all three are the 3 largest customers for the moment. As you could see also, the company grew very quickly from about 2006, although the company was founded in 1997. But the first big volume of PV modules were produced in 2006. The growth in terms of revenue grew very rapidly until 2011. And as you all know, the price of PV module went down very quickly during that time, which means that even if the volume continued to grow, the revenues for the company decreased in 2012 and grew back again in 2013 due to the rapid increase of the PV market for the second half of last year. We have roughly about 17,000 employees. Most of them are in Changzhou, China. And the rest are distributed around about 22 different offices around the world. The office in Australia is based in Sydney, and Douglas Smith is our country manager here, and he's here. And Esther Lee was studying at UNSW before and work also for Trina, one of our representatives here in Australia. Okay, so question now, going to the topic of this presentation: where is the industry going? People usually look at the worldwide PV market in a linear scale, and I like to present it here in a logarithmic scale because it's much more interesting to see what happened between the years between 1970s and 2010. And you could see that in logarithmic scale, it's pretty much a straight line. When I started working in PV, the worldwide PV market was less than a megawatt. And there were a few companies with a megawatt capacity, and that was huge. Today, you would consider a significant PV module factory of several gigawatts, and everybody's going towards 5 gigawatts and even more. So this is interesting. If we continue the growth, and here there are three different projections, 25, 30, and 40%. I don't think we'll continue to grow to 40%, but 25% is quite realistic. But if you continue extrapolate from there, and when will we reach a terawatt per year? That's roughly about 2025 plus minus 5 years. The big question is, will we reach a terawatt per year market? And probably not. It's quite reasonable to think that the PV market at some point will saturate, and will saturate around a few hundred gigawatts. When? We don't know exactly. But it's not impossible that we'll be close to a terawatt per year. Interestingly, the growth of the PV market changed significantly over the years, over the last 40 years. And this graph represents the 5 years compound annual growth. So if you take your last 5 years and you look at the average growth during those last 5 years, it went from a quite significant growth in the beginning, decline steadily to about 10%, roughly in the middle of the 90s, and then grew rapidly here. That was due to basically the feed-in tariff in Germany. So we could say that pretty much we had 42 years of gestation between the first solar cells in the 1950s to the introduction of the feed-in tariff in Germany. Then we had the birth of the PV industry in 1996. We had the infancy of the PV industry, and now we are in the adolescence of the PV industry. And the adolescence is marked with a lot of questioning, a lot of trouble. We still need the money from the parents. We cannot stand on our 2 feet, but we think we grown up. Okay, so the big question is, when will we reach adulthood? And I think what do we need to do to reach adulthood? I think there are 5 conditions. These are the 5 conditions. Number 1, cash flow sustainability. It means that we need to generate enough profit that we are able to grow without borrowing a large amount of money and risking to be bankrupt if there is any downturn in the industry. So we need to be profitable, generate enough cash to grow. We need to reach a subsidization-free market. We need to be able to sell our product without subsidies. Okay? So that means that PV must be a no-brainer, an obvious choice, even without subsidies. The next one is material sustainability. What does that mean? It means that we need to make sure that we can grow this market up to the terawatt level per year without any problem for the environment and the availability of material. So we don't have any material supply issues up to the terawatt level. Energy sustainability. A lot of people have said that you consume a lot of energy to create a PV module that you will never pay back. We know that's a myth. We know that's not true. The problem is that we've been growing so much, so fast, that it takes a long time to pay back that energy, because we're growing faster than the time it takes to pay back the energy. So we must have a positive impact on the reduction of fossil fuel consumption. Okay, so it means that we cannot grow too fast, but also we need to reduce the energy payback time. And then finally, we need to have a good grid management sustainability. And what we see today is a lot of backlash from the utilities saying that it's not sustainable. We cannot increase indefinitely the presence or the penetration of PV into the electrical market or the electricity market. It's not sustainable for the grid. So the utilities have to change the way they operate the grid. We also have to think, it's our responsibility also to make sure that we provide a sustainable grid. So that means that PV must become a voltage source on top of a power source, and in a smart grid environment with efficient storage. Okay, so those were the 5 conditions to reach adulthood. Now, a lot of people have been using what it's called a learning curve model to predict where PV is going in the future. Unfortunately, the learning curve model has been used by many people to explain a lot of things, not necessarily in the right way. So it's important to understand exactly what it means. So this is the equation here in the blue rectangle. It says that the cost at a certain time equal to the cost at the reference time times the cumulative production at this time t divided by the cumulative production at this reference time with exponent minus b. Okay, so a few important things to remember. This is applied to cost, does not apply to price. The second thing, the parameters is the cumulative production, not your capacity, not the capacity of your factory, not the worldwide capacity, the cumulative production. And we're not talking about shipment, because you reduce the cost if you produce, even if you don't ship. Okay, so we have to distinguish between production and shipment, and you have to distinguish between cumulative production and capacity or worldwide annual production. So this being said, and if you keep that in mind, then we'll see a little bit later what that means. Then there are 2 terms that people have used. One is the progress ratio. It's basically the ratio in cost when the cumulative production double. So if the cumulative production double, 2 exponential minus b represent the progress ratio. And if the learning rate is 1 minus the progress ratio, so basically in PV, people will say PV has a learning rate of minus 20%. Okay, so that means the cost of manufacturing PV reduced by 20% every time you double your cumulative production. Okay, so let's look at what that means for PV. And you probably have seen this curve many times. Some people have called it the Swanson's law, which is not the right term, because Swanson has not invented anything here. The learning curve existed for a long time, and he was not the first time to mention it in case of PV. But he's been at least one of the most proponent of the learning curve model for PV. So this represents the price of an average power PV module over the years in a constant US dollars of 2011. Okay, so remember, this is now price, and this is an average module and it's a power module. So we're not talking about small module. We're talking about modules of 250 watt, for example. Okay, and of course there's a lot of noise because you have different producers, you have different countries of origin, you have a different type of modules, monocrystalline, polycrystalline, etc. So if you want at a certain time say what's the average price, it's quite difficult. Okay, so there's a lot of uncertainties in this curve, but really this is this curve and represent roughly the average price of PV module over the last 40 years. In the axis you have the cumulative production. Again, this is not the cumulative shipment or the annual production. Okay, and this is a log-log plot. So in a log-log plot, if you look at this equation here, if you put a log-log plot of this equation, you should get a straight line, and effectively this curve is roughly a straight line here with the equations that is represented here on the graph. Okay, so we could put a few dates on this graph. 1975, so that's pretty much as far as we can track the price of PV modules. 1990, it's representative of the end of the Ronald Reagan era. 2000, this is the when the technology bubble burst. You see it has absolutely no effect on the PV industry. 2003, for the first time in the history, in 2003, the PV industry consumed more silicon than the semiconductor industry. It's an important event because it will dictate what happened next over the following 5 years. Actually, over the following 10 years, pretty much. And although this event had been predicted for about 25 years before it happened, pretty much nothing has been done because the silicon industry was waiting for the price of silicon to increase to start investing in capacity of producing silicon feedstock. And that's why we see this huge increase in silicon feedstock price, which makes, at this point, the PV industry entering a market that it's called a supply constraint market. And when you're in a supply constraint market, what's happening is the price increase usually. And that's what's happening here. Between 2003 and 2008, the price of PV module increase or stay more or less constant. In 2008, we enter into the global financial crisis, and there's a slowdown in the PV industry, which makes the industry realizing that we are in overcapacity mode. And it's not unusual when you have a market growing at 40 or 50% and it takes more than a year to build a new factory. It's normal that at this point people are running with a capacity that is 50% or 100% larger than your production level. But when there is a slowdown in the industry, that becomes a dramatic event. And that's exactly what happened. Between 2008 and 2011, we had a huge drop in the price, module price. Okay? And we go very, very quickly, and that's quite unusual in the market, where the market goes from a supply constrained market to a demand constrained market. And when you go to a demand constrained market, the price of a product goes below what the learning curve model, which is the straight line. Okay, so price goes down. So at the end of 2012, we were pretty much at the end of this curve here. So we have a learning rate of 20%. That's you have heard that many times probably. PV has a learning rate of 20%, which means that in this case, the price in average goes down by 20% every time you double your cumulative production. Now, so this is price. Now, what happened to the cost? And if you assume that there is an average gross margin of 30%, the red curve here represents the average cost of production of PV modules. But of course, the gross margin was not always 30%, and of course it was not constant, and of course the cost did not follow exactly that red line, but something around that red line. So what you see right now, we are in a situation where pretty much the PV industry is running at least in the end of 2012, at zero gross margin, which means at loss. Okay? The big question, what happened next? And we already at the end of the beginning of 2014, and we know already what happened. But anyway, this is what was predicted, and I'm glad to see that exactly that's what happened. Would the price keep going down? And of course, you could see from this graph that's not possible. The industry will not survive. Okay, it's pretty clear. You could run for some period of time at zero gross margin, but you cannot run for a long period of time at negative gross margin. Would the price of PV module now shift to a parallel line, parallel to the original learning curve model, but below? Some people have predicted that, and as you could see, it's not possible either. The industry, if this model is correct, if the industry is capable to reduce its cost at a certain rate that is fixed because it's a fixed technology, then this is not possible. The industry cannot run for a long period of time at zero gross margin. Would the price increase? Yes, it has increased this year, and it's quite possible. And there are some reasons why that could happen. Although it will not happen as fast as it's represented on this graph, because that will completely collapse the PV market. So the most probable scenario is that the price of PV module will stay more or less constant for a certain period of time until we reach the historical learning curve of price, which is represented by the black line. And then we keep going down and following the cost with plus a certain markup. So this is the most probable scenario. The main question is, when do we go back to this point here? We are here right now. This is end of 2012. We are roughly here at the end of 2013. When will we reach the point where we go back to the black curve? And then you could calculate that if you estimate the growth rate of the PV market. So if you suppose that you grow between 25 and 40% from now to that point, this point will be roughly between 2017 and 2019. So it takes a long, long time. You see that this point here, just right here, corresponds to 1,000 gigawatts of cumulative production. And today we've got something like 200 gigawatts of cumulative production. So we need to produce 800 gigawatts additional before we reach that point. So it's not a beautiful story. It takes a long time to recover. Now, that may not be the only scenario. Like I said, we went from a supply constrained market to a demand constrained market, and we could go back again to a supply constrained market. Okay, the one we've seen between 2003 and 2011 was due to the silicon feedstock supply. Which material could be at risk? The most probable will be silver. Okay, and I'll show you that in a few minutes. Okay, is that model correct? Okay, cost reduction analysis. So I went back to the cost of producing module between the beginning of 2008 till the end of 2012, and this is not just Trina data, but it's data for the overall PV industry in China. Okay, so the average sales price between the beginning of 2008 and the end of 2012 went from $4 to 0.73. So we reduced that price by 81%. The cumulative production in the same period went from 13 gigawatt to 150 gigawatt. And that includes not only all the modules that have been shipped, but also all the modules that were in warehouse at the suppliers, at the producers, at the distributors, retailers, etc. So we have a ratio of about 11. So from the learning curve, knowing the ratio, we should have had a price reduction or cost reduction of minus 53%. Okay? So what was the real cost? That's the big question. Okay, so I'll look at the production cost of multicrystalline. I did the same for mono, but I'm presenting here the data only for multicrystalline. In 2008, we were in a very abnormal situation where silicon feedstock was huge, a huge proportion of the overall cost of the module. Represented 54%. We're now today in a situation where silicon feedstock represents 20%. The wafer itself, including silicon feedstock casting and wafering, represent almost 50% of the cost of the module. Then we have the cell 23% and the module 35%. So we were in a very abnormal situation. Here we are much more normal distribution here in function of cost, and we had in reduction in price minus of course minus 70%. Okay, so if you look in this graph, the red line represents the reduction in price. So the ratio between 2012-2008 was minus 80%, so 18% here. The yellow line represents the learning curve model, 46%, and 29.9 represent the actual production cost reduction. Okay, so this is for total, but because we were in a very abnormal situation where silicon feedstock were very expensive, it's interesting also to look at the non-silicon cost. Okay, and if you could see that the non-silicon cost, the ratio between end of 2012 and beginning of 2008 is 51.6%, which is very, very much in line with the learning curve model of 46.7%. Okay, so basically, if you exclude the silicon cost, silicon feedstock cost, basically all the learning curve model is being validated over the last 5 years, well, between 2008 and 2013. And you have, of course, a big variation between the different components. If you have silicon, casting, wafering, cell process, and module, you see there is a big difference between the cost reduction of those different components. As you could see, silicon feedstock costs have reduced dramatically by 90%. Casting reduced by 70%. Wafering reduced also by 70%. However, cell processing only reduced by 25%. And module costs only reduced by 40%. Okay, so you see a major difference in the different components in the fabrication of the module. Now let's look at some of the details. For example, in the casting components, big costs are the crucible, the graphites in the big furnace, and you see that the crucible cost reduction pretty much in line with the learning curve model, but there's been an enormous decrease in consumable cost of the graphite. Wafering, the major components are the silicon carbide, the propylene glycol, the wires for the wire saws. Okay, and all of those components have reduced dramatically over the last 5 years. Cell processing. I showed you before the cell processing cost has only reduced by 25%, so it's not in line with the learning curve model. There's a few components that you have to point out. For example, back silver and back aluminum. The consumption of those materials have been reduced dramatically. However, the front silver, even with the reduction of quantity of silver deposited on the wafers, the cost has increased by more than 5%. And this is mostly due to the increase in the cost of silver itself. In the module fabrication cost, pretty much all the components are in line with the learning curve model, the J-box, backsheet, EVA, glass, etc. The aluminum frame, unfortunately, has not reduced, and it's a major component in the cost of the module. If we're looking also at other components that are more general into the production floor, the electricity, although the amount of electricity that is used to produce a module has been reduced dramatically, the cost of the electricity has not reduced as much, and we have a reduction of only 35%. However, as you could see, the amount of electricity of megawatt hours per megawatt of module produced has been reduced by more than 65%. The water consumption also has been reduced dramatically in the range of about 63%. Labor cost has increased by 33%, however. So, what are the future challenges for the industry? Well, the first one, we talked about financial sustainability. We need to generate enough cash to grow. So how fast can we grow, or how much cash do we need to grow? What's the gross margin do we need? It's a major question. The faster we want to grow, the more cash we need. There is a basic equation here that's represented in blue. The growth of the PV industry is limited by the average sales price, the average cost of construction, and the EBITDA. EBITDA is the earning before interest, tax, depreciation, and amortization. Okay, so it's basically the amount of cash you generate in your business. Okay, if your price of ASPs, if I take a round number, easy to figure out what I mean. If I take an average sales price of $1 per watt, and the average cost of construction of my new facility is $1 per watt, and if my EBITDA is 10% of my revenue, I could grow only 10%. If I want to grow 20%, I need to have a 20% EBITDA. If I want to grow 30%, I need to have 30% EBITDA. So that's represent the financial difficulty of the PV industry over the last 10 years. We've grown so fast, and we have not generated enough cash to grow. So we had to borrow a lot of money. Okay, and we end up with the industry, with companies owing something like $2 billion, $3 billion, etc. Okay, so if we want to be sustainable, we need to generate enough cash to grow. The second condition, and we talked about energy sustainability here, if we want to grow, we want to make sure we don't have a negative impact on the consumption of the fossil fuel generated energy. Okay, so for example, if the energy payback time of a module is 1 year, we cannot grow faster than 100%. If it's 4 years, we cannot grow faster than 25%. Now, often the energy payback time is calculated in the best condition, when the panels are installed, for example, in Phoenix, Arizona, or in the middle of Australia. But what about if the modules are installed in London, Hamburg, Beijing, etc.? So the energy payback time of a PV module depends also on the location and how and where it's been installed. So if energy payback time of a PV module is 2 years, in Berlin it will be 4 years, for example. And we need to take that into account. So if we grow faster than 25% and most of the modules are going to Germany, then we cannot grow faster than 25% without having a negative impact on the fossil fuel consumption. Talking about material sustainability, and I said earlier there might be a problem with silver. This graph represents historical and projection of worldwide consumption of silver. The red curve is the total production of silver. The green curve is the industrial use, including PV. This blue curve corresponds to jewelry. The dots here, yellow dots, represent silverware, and the light blue here represent coins and metals. Okay? These blue curves here represent the consumption of silver for the PV industry. We consume roughly about 29 tons of silver for every gigawatt. Okay, depending, some people consume more than, some companies consume more or less, but roughly about 29 tons plus minus 5 per gigawatt. So today we're consuming more than 1,000 tons of silver just for the PV industry. If we suppose that the PV industry continue to grow at 25% per year, this blue curves here will go over any other consumption by roughly about 2020, and it's going to be the only fast-growing component for all the industrial use. Okay, and we already represent 10% of all the industrial use of silver. So it's not improbable that silver will be a problem for PV in the future, so we need to look at it very carefully. I'd like to point out the pink curves here represent the other consumption, and the other consumption includes speculation. It's interesting that those peak value here and here and here represent the time when the cost or the price of silver went up very rapidly. So this pink curve there represents speculation. I put a straight line here, but it's not improbable that we'll have a speculation of silver in the future also, which will bring peak of cost. This represents the price of silver over the last 13 years, 14 years. And you could see that in 2011 we have a huge peak here. Now we're back to more normal values because speculation has disappeared, but as PV industry is growing again very fast, we'll see some speculation there. Okay, opportunities and strategies. Okay, what we have seen in the market last year is a major change. Before, a lot of customers were looking for the cheapest module. Where is the cheapest module? Where is the producer of the cheapest module? And today what we see is that everybody is offering pretty much the same module, pretty much at the same price. So the customers are looking for quality. Which producer is giving me the best quality module? Which one do I believe gives me a 25% warranty and that company will survive? So there's a shift in the criteria of selection by the customer. People are looking for quality, reliability, and are certainly much more interested in LCOE, so the levelized cost of electricity. Of course, they all negotiate on dollar per watt. They all want to have the cheapest dollar per watt, but as soon as they're home, they do their homework, they calculate what's the LCOE. because they ask also what's your dollar per watt and what's your PAN file. PAN file is the input data for example, for the PV-Syst simulation software. So they go home and they simulate the energy and they calculate what's the LCOE. Okay, so they're really looking at that. And that's been a major shift in the industry over the last 12 months. Okay, so what is LCOE? It's basically the total cost of your system over the lifetime of the system divided by the total produced energy. So to get a low LCOE, you need to have high energy production rate. Okay, not necessarily high efficiency, but high energy production rate, so low temperature coefficients, for example. You need high reliability. You don't want that energy to decrease from year on year. And you want a low cost of installation and low cost of maintenance, operation and maintenance of your plant. That gives you a low LCOE. Now, if you look at the overall cost of a system, the cost of the PV module represents a relatively small part. You could get a PV module for about 70 cents a watt, roughly. You get an inverter for about 23 cents a watt, and you install a system for about $2 per watt, depending. With every country has a different labor rate and different price structure, but typically the PV module represent in the range of 30% of the overall PV system. And don't focus here on the real values of the system cost, module cost, because that changes very much from country to country. But what's interesting is that in this price structure, this is the module, this is the inverter. Those two here, which are basically labor, installation labor, and then cable racking, etc., attachment to the roof or attachment to the ground, all of those costs are proportional to the area of your PV system. So if you increase your efficiency, even if you increase the cost, the overall cost of the system decreases. Because if you increase the efficiency in dollar per watt, those values decrease because they are proportional to the area of the system. Okay? So, for example, this is represented by this graph. If you calculate the LCOE for a particular location, and this is, of course, depending on the dollar per square meter of your module and the efficiency, today, pretty much everybody sits around this star here. We have a module that's typically around 15% efficiency at the module level. The cost is in the range of $110, $115 per square meter. And in a good location like Australia or the US Southwest, you get something around 9 cents per kilowatt hour, typically. Now, how do we get down to 6 cents per kilowatt hour, which is considered as a target to compete with gas turbine, for example? Then you have the choice to stay at the same efficiency and reduce your cost of the module. But you have a long way to go because the module represents only 30% of your system. So you need to reduce your cost of your module by more than half. However, if you increase your efficiency and you decrease a little bit the cost, then you could reach your 6 cents per kilowatt hours very rapidly. So this travel here from this point to this point, it's much simpler than going from this point to this point. And it's also much more realistic. Another way to reduce LCOE is to increase the reliability, improve the reliability of your module. This is an example simulation of LCOE for a particular location, for a particular system cost, and this is relatively high, but it's typical cost in US for the moment. And as function of the performance degradation of your module, most PV manufacturers these days, and this has been confirmed by a study by NREL, the degradation of crystalline silicon is in the range of 0.5% per year in average. Most people guarantee minus 0.7, okay, and 25 years lifetime. So you can have a LCOE of less than 9 cents per kilowatt hour. But what about if you have to replace your module? What about if your degradation is 2% per year, etc.? So that has an impact on LCOE, and you could see that your LCOE in the worst condition could increase by more than 20–30%. So if you have a large degradation of the performance of your module. So it's very important that increasing reliability of the module, which means durability, but also the degradation over the years. So how to combine high reliability and low LCOE? It is clear that nobody, not a single PV manufacturer, can guarantee the best module, the most reliable module at the lowest cost. It's impossible. Nobody can do that. But today, modules are designed to operate from Adelaide to Berlin, go to Shanghai or Beijing or Tokyo or Cairo. Or the modules are designed for global installation. And for that reason, many of those modules are over-dimensioned, over-designed, over-engineered for very harsh climate. And they are designed to sustain any stress for any type of climate. And we know that we have around the globe very different type of climate. We have tropical climate, we have desert type climate, we have tropical, we have temperate, we have mountain climates, and the stress are very different in terms of humidity, UV exposure, thermal cycling, etc. So what's possible is to design modules that are extremely reliable for a particular climate without having to design it a reliability for any climate. And that's what's going to happen in the future. More and more standards will be designed for a qualifying module for a particular climate. And so it's important that we offer a reliable product with a excellent or better energy efficiency, not necessarily power efficiency, but energy efficiency for a particular climate to lower LCOE. So this is an example of 4 different climates. Here we have in blue a typical temperate climate, in green a typical tropical climate, in red a typical desert climate, and in mauve or purple a typical mountain climate. And you could see the distribution of energy over the year and intensity is quite different. And if you classify those different climates, you could see some of the, in terms of humidity or in terms of intensity. And intensity, in this case, I would consider the 50 percentile of the intensity of that irradiation. So for example, if I take the temperate climate, the 50 percentile is about 500 watt per square meter. Although the module has been designed for 1,000 watt per square meter. Okay, so the module is over-dimensioned, over-designed for that particular climate. It will never see 1,000 watt per square meter. Or very, very rarely when you have the situation where the sun is in the middle of a lot of white clouds and you have a lot of intensity suddenly, but that doesn't last very long. Okay? So you could class those different climates in this graph, for example, where you have temperate climate, where you have relatively high humidity but low intensity as the 50th percentile of irradiance. You have tropical climate with a very high percentage of humidity, of relative humidity, and more intense irradiation. Mountain, where you have very high intense radiation, particularly in UV, or desert region, for example. And the color of those circles representing the average temperature of that the module will see. Another way to reduce LCOE is to focus on energy, not so much on power efficiency or STC, and energy produced by the system. So power optimizer is one of the solution. And in this case, Trina has introduced a product called Trina Smart. It's basically a PV module that is integrated or embedded into the junction box. There is a power optimizer, but on top of that, it's actually full product. It's a power optimizer, it's a monitoring device, it's also a smart curve device. Smart curve is a system to increase the number of modules you could have in a string. An inverter has a maximum DC voltage that you could apply to it, and the maximum number of modules is determined by this maximum voltage acceptable by the inverter divided by the maximum VOC of your module that you could have at the minimum temperature of this particular location. So, however, the module will never go at VOC, or almost never. So the smart curve is basically a device that will chop the IV curve of the module to a voltage that's just a little bit higher than the VMP. And so you could put 20 or 30% more module in one string and reduce your cost of balance of system. And then the final device that's integrated into the junction box, it's a safety switch disconnect. So the module could be disconnected automatically if you lose the grid, but also if the fire departments decide to turn off your system. In this case, there will be no DC voltage on the roof, and they could spray water on the roof of the house, for example, in case of fire. So this is a product that you could integrate into the module. It doesn't do anything to increase the STC of the module, but improve the energy production up to 20 or 25%. Increasing the efficiency is it's a way also to reduce LCOE. Like I said before, that's because the PV module represents only 30% of, roughly about 30% of a PV system. So if you increase the efficiency, you reduce the area for a fixed power output of your array. So it means that you reduce your transportation cost, storage cost, installation cost, racking cost, cable cost, etc. Also, what you do, you reduce your temperature coefficient. So you improve your energy efficiency of the system, because the temperature coefficient is directly related to the voltage of your solar cell, the VOC of your solar cell, the VMP of your solar cell. And so if you increase your efficiency, basically the highest parameter, the most important parameter you play on is the voltage, and by the same time you reduce the temperature coefficient of your solar cell. So this is a IV curve of one of the R&D cells that we're working on. So that's a PERC cell that we're developing right now at Trina. It's 20.5%. Increasing the durability and increasing the reliability and reducing the degradation per year. It's extremely important also to improve LCOE. And that is done, in this case, with using double glass module. Double glass modules are extremely reliable, much more reliable than a module made with glass and backsheets, because backsheet is responsible for water vapor going inside your module, and is responsible for a lot of reliability issues, including black lines, including PID, including delamination, bubbling, etc. The backsheet also risk UV degradation, becomes more brittle over time, could crack, could create bubbles, could delaminate from the EVA, etc. Not that it happens all the time, but it happens sometimes over a long period of time, and particularly under very high stress, for example, very high UV exposure. So double glass modules are extremely reliable, and so far, of course, we don't have 25 or 30 years experience with double glass module. Not at Trina, but double glass module have existed for a very long time. Shot Solar had double glass module way before it was actually called Shot Solar, and those modules are extremely reliable. So we believe a lot in double glass module as a way to reduce LCOE by mostly improving reliability. Okay, sustainability. It's not all about cost. It's also about sustainability for the earth. So reducing the energy consumption, but also reducing the water consumption, reducing your carbon emission during your production is extremely important. So at Trina, we, for 2 years in a row, we have been #1 for the SVTC Solar Scorecards. So SVTC, it's a Silicon Valley Toxic Coalition, and we have been nominated #1 two years in a row for our contribution in reducing our environmental footprint in the production of PV. We reduce water and electricity consumption by 65% over 4 years, and carbon emission reduced by 25% during the same time. Also, the carbon footprint has been verified by the British Standard Institution. And if you look at the graph below, you see the comparison of Trina solar panel compared to coal, representing roughly about 1,000 grams of CO2 per kilowatt hour, 900 grams of CO2 per kilowatt hour for oil, 580 for gas, 85 for nuclear, 19 for PV. Okay, so it's a major impact on the environment compared to the other source of energy. It's very important to keep that in mind. Conclusion, the great price decline of PV, it's over. And that's probably a bad news for the customer, but it's certainly a good news for the industry, I think. However, the recovery will take a long time, and we have to be aware of that. The average sales price dropped by about 80% between 2008 and end of 2012. But the manufacturing cost has only reduced by about 70%, and mostly driven by the silicon feedstock, which means that the PV industry is today with a very low gross margin, and it was almost zero at the end of 2012. But the learning curve model is quite has been validated if you exclude the non-silicon cost. Major cost reductions being in silicon feedstock, casting, wafering, backside electrode. Minor cost reduction being achieved in cell processing and module assembly. Cost increase being observed in labor, and even in China, labor rate increased very rapidly. So we need to take that into account. And the silver cost is increasing. Challenge for the industry, regain profitability, have a sustainable growth. We need to have enough gross margin. We need to have a low energy payback time. That's for sustainable growth. And we need to develop a silver-free process if we want to grow into the terawatt level or close to the terawatt level in the 2020. And 2020 is not so very far away. And when you look at the time it takes to develop technologies and qualify it and convince the market this is the right technology, this is very, very close. Okay? Opportunity, we need to focus more and more on reliability and reducing LCOE, develop reliable products and with a high energy efficiency for a particular climate, we need to reduce the energy payback time and the carbon footprint. That's it. Thank you very much. I should have said you could ask questions during the presentation, but please do now.
We're almost out of time, but if anyone has a few questions.
Yes.
I was wondering if you know, well, does Trina, for example, give the degradation rate specifications on its panels, or is there a standard to compare reliability of different module manufacturers?
Okay. It's very difficult to have real data. Of course, we have testing, we have thermal cycling, humidity, freeze, damp heat, etc. How does that relate to the real degradation, the real world? Well, it depends very much on the climate. You're not going to have the same degradation in Alice Springs or in Shanghai. Okay, so there is not one answer for one module. There's a multiple answer for depending on the climate. Even there, we don't know that relationship because we don't have enough time. Our modules, our first modules have about 7 years now of lifetime in the field. Okay, so far it's been excellent. Much better than what we guarantee. So we guarantee 0.7% degradation per year maximum, and so far it's been excellent, much better than that. With the double glass module, the testing we've done in-house in accelerating testing, and we've done TC600, and we're doing TC800 pretty soon. We've done DH3000 so far. We've done humidity freeze up to 50 cycles. So we're talking 5 times the kind of testing that you do for IC61215, and we see much less degradation than a standard module. So our guarantee for a double glass module is minus 0.5% per year. Or lower than that. Now, the question is, can you prove that with field data? Not yet. Okay, so that's the big question.
That's what I wonder. You say it's of such increasing importance to customers now, but how?
So the maximum number of data we could give you with our product is 7 years. Yeah. Okay. Yep. Okay, I think we are first.
Your learning curve model captures a bunch of things in addition to learning, one of them being manufacturing efficiency at scale. Do you see the same gains in manufacturing efficiencies at scale going forward as we've seen in the past, or are those gains, have they been realised? Do you have a view on that?
The theory of the learning curve model, and it applies not only for PV, it applies for anything you manufacture. It does not apply to product you extract from the ground. It does not apply to services. But for manufacturing, the learning curve model extends for theoretically forever. There's no reason that it will change. The learning rate changes over time. There is no indication or there is no theory explaining why it would change over time or would go down to zero. Some people have explained what happened in the market by saying, oh, the learning rate has changed. It went from 20% went to zero for some time and then went to 80% at another time. This is not true. The learning rate doesn't change. What they were trying to explain the price with a learning curve model, and the learning curve model does not apply to price, it applies to cost. Okay, it just tells you that you reduce costs by doing, you're learning by doing. Okay, and the more you do, the more you learn and the more you reduce cost. And you could reduce cost by many, many different factors. This year it could be we reduce cost by improving productivity. Tomorrow or next year it could be we reduce cost by reducing the cost of materials, etc. In general, you do a little bit at a time altogether. But it will continue.
Do you think efficiencies of scale are going to drive costs in the future, or has that been realised?
So,
do you think scale efficiencies in manufacturing are going to drive cost reductions in future, or have those scale efficiencies been harnessed? Have they been?
Scale of manufacturing, so it means the capacity of your production line, it's only one factor. You could reduce cost even if you keep the same capacity, because the learning curve model says you learning by doing. So over the years, even if you keep the same production level, your price will improve. So the economies of scale, it's only one factor in the overall equation.
Do you have plans to create panels that are designed for a specific climate, like you mentioned?
Yes.
In the near future then?
You will see that very soon.
Considering all that you mentioned in terms of how we can improve, or how silicon technology has improved, can you see any contender that is not silicon based? Because even if we increase the efficiency, let's say with a tandem device, that it doesn't apply us with silicon because we cannot keep the cost of the material as low as with silicon. So is there any technology that you can see that can compete with silicon in terms of being another option for PV?
Yeah, there are several options. I'll take one example. CPV, concentrators, doesn't use silicon. It uses multi-junctions 3-5s. They use, for example, mirrors or lens to concentrate the light. The theory, and if you put all the data together, shows that you could compete with flat plate silicon in terms of cost. For the moment, it has not succeeded, mostly because CPV never had a chance to demonstrate a technology, prove reliability, have a large-scale manufacturing, and go down the learning curve. But theoretically, if you imagine a field of solar cells, I mean talking megawatts of solar cells on a tracker, for example, for tracking the sun, and you compare that to the same field replacing the modules with mirrors, reflecting the light onto a central receiver that is about 1,000 the size of the solar cells, theoretically, this has to be cheaper. Now, will it ever happen? I don't know. For the moment, certainly not, because flat plate has such a huge manufacturing capacity, such a huge learning curve. For 40 years, that's reducing the price by more than 2 orders of magnitudes. I don't think that CPV will be able to compete for quite some time. But it's possible. Yes.
Can you please explain a little bit more on how the energy payback time affect on the industry? Because I feel it's not as obvious as like a cost cut down or cash flow or the other factors. It's somehow indirect for me. It's more political kind of argument thing. So can you explain a little bit more to me? Energy payback time.
Yeah, so you're talking how to reduce the energy payback time on the production side, or?
No, how does it affect on the industry, the growth of the industry?
For the moment, it does not affect the industry. really, because very few people think this way. And so if you don't think how long it will take to pay back the energy, it doesn't matter. And most people don't think about this way. But if you think that impact your cost of manufacturing, your energy cost is important, your water cost is important, your carbon cost is important, then it impacts the price of your product and impact your marketing and the way you sell your product. But I think globally we need to look at, as an industry, what is the impact do we have on the energy sustainability of this planet? Unfortunately, most of the PV manufacturers don't think this way.
Nor most of the consumers, otherwise they just stop buying coal and gas, everything else a long time ago.
Thank you very much again.